Thank you very much. Is my mic on? Yes. Is this, can people hear me? Okay, good. Great. Okay, yeah, so thanks for the simulating talk. We'll have to continue this wherever Gil went. We'll have to continue this afterwards. But for the moment now, I'm going to return to exploring the complexity theoretic basis for our understanding of quantum supremacy. So I want to very quickly recap what we did last time. So last time, what I described to you is that, a lot of the origin of these kind of intuition for quantum speedups, at least in this exact sampling sense, comes from the difference between gap P and sharp P. And I described to you this kind of reduction, that it's a reduction that transfers you from basically something where you're arguing about the difficulty of sampling, which we tend to have very hard time reasoning about. I gave some reduction. It's a BPP to the NP reduction that says that, well, instead of thinking about the difficulty of sampling from your experiment, then you can instead reason about the difficulty of computing, or maybe of approximating, the output probabilities of your quantum circuits. Namely, if you can show that approximating your output probabilities is extremely hard, much harder than BPP to the NP, then you can end up showing that an efficient sampler shouldn't exist. And what I ended with last time is I said, okay, well, if we now move to the case where we're talking about approximate sampling, then what we end up having to discuss over here is the difficulty of computing these output probabilities on average. So let me remind you with kind of what we ended with. So I'll state this theorem a little more concisely. What we wanted to say is to argue that that it's hard to sample from the output distribution of quantum circuits. In order to say it's hard to sample from the output distribution of quantum circuits approximately, that is up to L1 distance, error, then it suffices to show the following thing. It suffices to show that there exists some distribution D. This is a random on quantum circuit C. On quantum circuit C, such that it's sharp P hard or gap P hard, they're basically the same thing, to approximately compute the quantity, 0 to the n C, 0 to the n squared, on average over the choice of C. That is to say, if you pick a random circuit from the distribution, then it should be hard to compute the output probabilities of these circuits, even for typical circuits, and not just for kind of worst case circuits. And now you might notice that here I kind of did I pulled a little trick on you here. So the last time what we ended with is I argued that what we need to argue about is worst case circuit C and average case Y, that is average case output strings. But here, this theorem is talked about in terms of average case C and worst case Y, that is just some kind of fixed Y. And it turns out that there's kind of a technical aspect of this reduction which allows you to translate between these two. So actually, such that this, like showing something for, like basically there's a way of pushing the average case nature away from the output strings, which your simulator gets mostly correct, to pushing it toward the average case to the circuits. The basic way that you do this is you say, okay, if it's hard for worst case C and average Y, well, that would also mean it's hard for average C and average Y. That looks like a loss, like you're kind of making a a possibly lossy step of your reduction there. But it turns out that if you pick distributions over circuit C on which don't really have a preference for different y's. So namely, if your distribution over circuit C is invariant under, say, switching or permuting the y's that occur at the end of your circuit, then these things end up being equivalent to one another for many natural distributions. So this is called, like, Aronson and Arkhipov called this the hiding argument. But I'm not going to go through it in detail because it's really not where the technical meat is in the proof. The technical meat in this work is in trying to establish forms of approximate average case hardness. Okay. And what we ended with last time is we said something like, okay, let's say we plotted what we know about the hardness of computing output probabilities of quantum circuits. You know, let's say this left column is worst case, this right column is average case, and this is the hardness of computing them exactly versus approximate. So this difference between gap P and sharp P is what makes them hard to approximate in the worst case. Basically, all these quantum circuit families have this property. These are kind of like the freebie squares. And then our conjecture that we need for quantum supremacy for simulating to small total variation distance lives in this quadrant. We need this problem to be hard on average, and we need approximating it to be hard on average. Okay, so why should we believe this conjecture? So far, what's kind of been done in this area is people have been able to prove results in this quadrant. And the first result of this form came from a work of Aronson and Arkhipov from 2010 on boson sampling. What Aronson and Arkhipov showed is that for the boson sampling experiment, they showed that this actually is sharp P hard in this quadrant as well. So therefore, this means that conjecturing average case approximate hardness is not so crazy. Because it's kind of saying, well, we know it's hard to compute on average exactly. We know it's hard to compute approximately in the worst case. If we could somehow just combine the best aspects of both of these theorems, then we would have our average case approximate theorem. Okay, so how did they do this? It was actually very clever. So what they did is they noticed that certain physical experiments related to non-interacting bosons, and this is the experiment they're talking about, have the output probabilities of their circuits correspond to the permanence of matrices. So let me explain what the permanent is. Let's say that you have a matrix A, which is in some field. It's an n by n matrix. Then the permanent of A is equal to the sum over all permutations of n things of the product from I equals 1 to n of AI sigma I. So I'm going to contrast this with the formula you might know. This is a formula for the determinant of a matrix. The determinant you can write in this way as well. You can write it as exactly the same formula. You can write it as exactly the same formula, but where there's this additional minus sign in the formula. Right? And this minus sign is a -1 to the sign of the permutation. Now, it turns out that this tiny modification of this formula drastically changes the difficulty of computing this function of a matrix. So we all know, how do you compute the determinant of a matrix? Yeah, Gaussian elimination. You take the product of the eigenvalues, right? It's very simple. But on the other hand, there's a very nice result of a classic result of Valiant, which showed that the permanent is sharp P hard to compute in the worst case. In fact, it's even hard to compute it, say, over 0, 1 matrices. So this is kind of surprising because, all we've done is, maybe this is counterintuitive to my last lecture where I told you minus signs makes things harder. In this case, this minus sign actually makes things much, much easier. And the bosons actually do this task. But okay, so the starting point of Aronson and Arkhipov's kind of the genesis of boson sampling was, okay, they said, look, we know the permanent sharp P hard to compute, but we actually know much more than this. There's a classic result of Lipton from, I think it's from 91, which says also that the permanent is sharp P hard to compute on average. So what do I mean by that? Well, the original distribution that Lipton was talking about was actually talking about permanence over finite fields. So his argument was something like this. Let's say we pick a random permanent. So, okay, let's let D be the uniform distribution on F, Q, n by n. So here Q is some prime number. So this is, your entries are from the finite field where Q is sufficiently big. I think Q is only polynomial in n. Then the claim is that it's sharp P hard to compute the permanent on average over that. So what does that mean? That means, more precisely, if an algorithm A, I'll call it script A, if an algorithm script A is correct most of the time, then then it can solve sharp P hard problems. So I'm going to write that a little more precisely here. What I mean is that if there exists some algorithm A such that if you consider the probability over drawing a random matrix R from this distribution, then the probability that A of R is actually equal to the permanent of R. If this probability is relatively big, then that means that, then that implies that A can compute, there's a polytime algorithm that's almost the same as A, is it can compute any permanent that it wants. And therefore this is sharp P hard. So does this formalism make sense? It's a little weird, but it's saying, when you say that you have an average case algorithm, it's not saying you have an algorithm that works most of the time, and then when it fails, it tells you, it outputs failure or something. It's rather saying there's an algorithm that works, 99% of the time, and 1% of the time it's actually giving you wrong answers, but you don't know when, you don't know which 1% is wrong, right? It could be anywhere. And what you can view this result as saying, this, you can interpret this as a form of error correction. There's actually kind of a precise way in which you can phrase that, and you'll see when I prove this statement, you'll see what's going on here. But the reason you can think about it as a form of error correction is that it's saying, look, I have this algorithm that's correct on 99% of the output bits. It's wrong on 1% of them. It's saying, I can find the 1% that were wrong and fix them if I wanted to. Just like if you had, some message encoding in error correcting code, 99% of the bits are correct. You can correct the string to get back to the correct message. So, yes. Yeah, exactly. There'll end up being a polynomial here that allows you to do this reduction. So I'm going to give this proof next so that you kind of see concretely how this works for finite fields. Okay. So the proof of this is actually very simple. And the proof looks something like this. So let's consider some matrices. A of t. All right. Oh, sorry. So the base case is, let's say you suppose you want to compute the permanent of x. Now you could run your algorithm A on x and see what it outputs, but the point is A is only correct on average, so you can't trust it. You wouldn't know if it was giving you the right or the wrong answer. So how are you going to do this? Well, what you're going to do is you're going to find some family of matrices A of t, and you're going to let A of t to be x plus t times r, where r is drawn uniformly from this random distribution. Okay? Now, there are kind of a few key facts that make this work. So the first thing that you'll note is I've defined it such that, A of 0 is the matrix X that we want, right? And the next property is that the permanent of A of t is actually a degree n polynomial in t. So t here, remember, is taking its value in the finite field.
Is it a large field? You need it to be large?
Yeah. So I said Q has to be more than poly n. Yeah, that's right. If it's, yeah. Okay. So how can you see this fact? Well, you see this fact just by looking at this formula. So in this formula, you only ever take the product of n different entries of the matrix at a time. Now, each entry of the matrix of A of t is a monomial in t, right? It's some constant plus t times whatever the entry of R was. So if you take the product of n things of degree 1, it will be of degree n. And then you take an exponential sum of this, but right, exponential sums don't change degrees, right? Okay. And it has this other really nice property, which is something that I'll call the marginal property, which is that for any t which is not 0, mod q, we have this property that the distribution of A of t, over the random choice of R, is actually uniform. So what are these family of matrices? Well, you can think of them as a family of matrices which have the following property. Their matrices are all really correlated with one another, right? The first matrix is X. The next one is X plus R. The next one is X plus 2R. The next one is X plus 3R. They're extremely correlated with one another. But if you were just to look at one of them in isolation, it would look to you uniformly random, because effectively this matrix R is serving as a one-time pad, right? Like you're just one-time padding in a random matrix. All right, and the cool fact is that this is already enough to give you a proof of average case hardness. Actually, wait, I realize I can use the boards more fancily here. So then this is next to it, and that's probably better. Okay, so can anyone see the proof who has not seen Lipton's proof before?
Can you repeat that question?
Sure. So the question is, how can I show, so I'm trying to show if I had an algorithm that computes average case permanence, then I could compute the permanent of X. Okay, so now I've given you some family of matrices such that A of 0 is X. We have a low degree polynomial, and each element of the family looks random, even though it's not. So the key point here is that because of this marginal property, so maybe I'll give the next step. This thing I'm calling the marginal property, this, yeah?
Can you think of the R as like noise that you want to cancel out when you try to repeat?
Oh, yes, yeah. So the question is, can you think of R as noise that you're trying to cancel out? It's kind of, it's noise that's been added in a very structured way, and actually it's the structure that's going to help us here, actually. We're not going to cancel it. But, okay, I can describe it maybe, and this will make sense. So I'm going to now claim that this marginal property means that for any t not equal to 0, the probability that, over the choice of R, that this algorithm A works on A of t that this is more than 1 minus 1 over poly Why is that? Well, I just said that this distribution is uniform, right? And therefore, that means if I were to just look at whether the algorithm is correct on this one particular output, that means it has to be correct most of the time, right? Okay. But now there's some kind of subtle issue, which is that, if I'm, the basic strategy that we're going to do here now is that what we're going to do is we're going to run the algorithm on A of 1, A of 2, all the way up to A of n plus 1. And we're going to get its outputs, right? And the thing is that if the algorithm were correct every time, then we know we'd be set. So why is that? Well, that's because we have this low degree polynomial property. So if you have a polynomial of degree n, and you fix its value at n plus 1 points, then that uniquely specifies the polynomial. So, let's just write it. So if they were all correct, you could compute the permanent of A of 0 by, which is equal to the permanent of x, by, finding the unique polynomial P of t of degree n, where P of t is the permanent of A of t, which, as we said, has this low degree polynomial property. Okay. And now the really slick part of the proof is the next part. So, we run the algorithm on all of these different matrices. And we only know that the algorithm works most of the time on each one individually. So, but these matrices are all super correlated with one another, right? Like, this isn't like every one is independently random. It's rather the marginal in each one is random, right? So kind of the key insight here is that you can use a union bound to say that the probability that any one of them is incorrect has to be at most, n plus 1 times our probability of error. Right? The union bound just says if you have n different events that each fail with probability epsilon, well then the probability one of them would fail is at most n times epsilon. So if they were kind of correlated all together in the worst possible way, then this is what you could get. So you can now see that if you make this polynomial sufficiently small, you can make this less than 1 over poly as well. Right? So that's the proof. All right. So are there any questions about this proof? Did this make sense? It's very slick. So maybe it's worth kind of going through a bit more. Yeah.
So finally, what you get is that this A can compute the permanent with some probability of correctness, and then this. So you need the polynomial.
Yeah. So in the end, what you end up getting a BPP algorithm for the permanent. So I guess it's saying this problem is short p hard under BPP reductions. Yeah.
But the point is that the number of random bits is only on R, which is like the square of them. So if this polynomial is sufficiently large, it just means that it still will correct with probability 1.
No.
Adam,
So
Adam, can you repeat the question?
Yeah, sure. So the question was, am I trying to use some tricks with the number of bits we're flipping to argue that this algorithm is always correct? No, I'm not. This algorithm will fail a tiny amount of the time. So that's why I'm saying this is a randomized reduction. So that's why I mean a BPP reduction. But I mean, if you could compute the permanent on average in P, then there would be an algorithm that computes the permanent in the worst case with high probability. That is to say, there would be a randomized algorithm that computes the permanent. And that is also not something that should exist as well, like a polytime algorithm. So maybe, yeah, the technical statement would be that computing the permanent on average is sharp p hard under BPP reductions. Yeah, sure. Okay.
I'm not quite understand. So under assumption that you can compute the permanent, so then you can compute the
Oh yeah, so the question is, I'm saying under the assumption you can compute the permanent, I'm saying you can compute the permanent. Yeah, that's, I'm saying, all right, so I'm trying to argue that no algorithm can compute the permanent most of the time. And remember, that's what we're trying to, in the quantum supremacy proof, we're trying to argue that you can't compute most, the output probabilities of random quantum circuits most of the time. So trying to show something is hard to do most of the time is usually much more difficult to establish than something that's just hard to compute if you could compute every single instance. So what we're really saying here is that there's some distribution on instances that's hard, kind of like a cryptographic problem. Like it's not just hard to solve all of the instances, it's hard even to get some fraction of them correct. Yeah.
If someone finds a formula relating the permanent is the determinant, does this proof have no value? For example, if someone finds a way to compute
Sure.
permanent using the
So the question was, if someone finds a way to compute the permanent using the determinant, then would this have implications for complexity? Well, yeah, if it were a polytime reduction, of course, it would collapse P to sharp P. But what you're getting at is actually you're starting to head in the direction of geometric complexity theory, and there's a whole field dedicated to this. So I'll point you in that direction. Sorry, can you compute what? Okay, the question was just, can I repeat the argument for the correlated case? So the statement is that all of these matrices A of t each individually look random, but they're correlated with one another. So in order to bound the probability of failure of this algorithm, we have to take into account the fact they could be correlated. So we'll use a very coarse bound called the union bound, which just says that if you have n events that occur with probability 1 minus, if you have n events that exceed with probability 1 minus epsilon, or let's put it in terms of failure. If you have n events that fail with probability epsilon, then the probability one of them fails out of any of them is at most n times epsilon. So I didn't use the correlation at all. The union bound is agnostic as to whether the events are correlated or uncorrelated. Right? If they were uncorrelated, the probability any of them correct, any of them was incorrect, would be like 1 over poly.
I mean, you use the correlation in the construction, right?
Yes, yeah. The correlations are there in the construction. So yeah, that's the short answer. I'm using the correlations in the construction, and I really don't know how the algorithm would behave under those correlations. So I'm using a very coarse bound to say the algorithm will still work kind of regardless of the correlations I introduced. Yeah. But you can kind of see, like more broadly what's happening here is we're saying something like this. This problem is very structured. It has this low degree polynomial structure. This structure you can think of like, if you know error correcting code, it's almost like, it's like a Reed-Solomon code that's hidden in the structure of the permanent. So what we're doing here is we're doing like Reed-Solomon decoding. And in fact, using that intuition, you can improve these hardness results a lot. So there were, Lipton's proof tells you it's hard to compute with probability more than 1 minus 1 over poly. But there are subsequent improvements to say it's even hard to get half of them correct. This is a result of Berlekamp-Welch. And it's even hard to get 1 over poly of them correct. So even if you have an algorithm, so this is a result of Sudan, and there are other authors there using list decoding techniques, so fancy error correcting code techniques. So in other words, what these kind of results said is like the permanent is kind of ridiculously hard to compute. It's saying even if you had an algorithm that only computed the permanent 1% of the time, 99% of the time it outputs garbage, even that cannot exist, right? So this is a kind of hardness that we don't know how to show for, say, NP hard problems. So, yeah.
Is it easy to compute the polynomial at t equal to 0 because we have exponentially many terms?
Okay, so the question is it easy to compute the polynomial at t equals 0 because there are exponentially many terms? So it's very true that this polynomial is natively a polynomial over the entries of the matrix. So there could be a lot of different monomial terms there. But the kind of really clever part of this reduction is that we actually reduced it to a univariate polynomial. It's a polynomial of degree n in a single variable, just the variable t. So we've kind of taken that really big polynomial, which is too high monomial degree, and we like projected it down to just a single variable. So now if you have n coefficients, yeah, there are only n plus 1 coefficients of this polynomial. That's all you're computing. Yeah. Yeah.
One question in order to know if I well understood. So you either are proving that there is a quantum supremacy or that the permanent is hard to compute, but could be the case that the permanent is easy to compute and we humans don't know how to do it?
I'm not sure I understand. Like,
could be the case that the permanent is easy to compute and the assumption that it is hard to compute is some problem in our mathematics?
Oh, sure, yeah. So it could be the case. That's kind of what we're hoping with this conjecture. We're hoping with this conjecture that it's hard to approximate on average. We don't know how to prove that. We're hoping that some future people will make a proof of that form. But at the moment, we're conjecturing it. But in this quadrant, for exact average case, we can prove it's hard to compute on average. This is the proof. It's Lipton's proof. Okay. All right. And just to, and the contribution of Aronson and Arkhipov is they ended up extending this. They extended this to the case of permanence of matrices, which are drawn from the IID Gaussian distribution. And I gave this as an exercise in the problem sheets. I realized there are no more problem sessions. But if you're interested in looking at this at home, you can see if you can generalize it to the continuous case. It turns out that there's a way of doing so. And it looks very similar to this proof, but there are a few tweaks that have to be done. And that's what Aronson and Arkhipov observed. OK, so I'm now going to move on. So let's fast forward in the history of quantum supremacy experiments to get to the Google experiment. So Aronson and Arkhipov proposed this experiment in 2011. And there were a huge number of works which tried to prove this result, which tried to experimentally implement boson sampling. And essentially what happened is that boson sampling ended up being a somewhat difficult experiment to perform. So to date, for a long time, the largest boson sampling experiment that was performed was with 6 photons, which by some things I haven't explained corresponds to computing the permanence of 6 by 6 matrices. Now the problem is it's actually quite easy on a classical computer to compute the permanence of a 6 by 6 matrix. So this did not seem like it was kind of going to be the first experiment that challenges the extended Church-Turing thesis. Now, just within the last few months, there was an experimental effort by the Pan group in China that did boson sampling with essentially with 14 photons. They even did some 20 photon experiments. So there's recently been progress here. But that's what kind of happened in the meantime is that back in 2016, people started making progress on superconducting qubits. So what happened then is that the kind of people who were involved with producing superconducting qubits, namely the Google UCSB group, said, well, why don't we propose the analog of boson sampling for our device? And this is the reason that this paper by Boikshow et al., by the Google group, they proposed something that they called quantum random circuit sampling. And I'm going to claim that this is the quantum, and this is kind of an analog of boson sampling. So what was the experiment? The experiment that they proposed is something like this. So they said, okay, let's take some pattern of qubits, and let's consider applying gates to these qubits, because in superconducting systems, they have qubits like kind of the ones you would expect, like the ones we've been talking about in this class. Okay, so here's what they said. Let's consider taking a quantum circuit. It initially begins in the all-zero state. Then let's say that we're going to take this all-zero state and apply some gates to it. In particular, we're going to apply gates in a really particular pattern. Let's call these gates G1, G2, G3, etc. The idea is that we're going to pick, we're going to fix a pattern of gates. And then what we're going to do is, for each gate, we're going to pick it uniformly at random from the space of 2-qubit gates. So, and namely, we're going to pick it from what's called the Haar measure on 2-qubit gates. So this is, the Haar measure is kind of the unique left invariant measure on the continuous space of 2-qubit gates. It's really what people mean when they say they pick a random gate. This is, in some sense, a truly random gate. And then what we're going to do at the end of the experiment is we're going to sample a string from this output distribution. Okay, and all right, so is the experiment clear? So the experiment is just, we're kind of fixing where the gates are going to be applied and sampling them at random. So it would be like, well, okay, one random choice, I could do a C0 here, a controlled rotation, the Bell basis here, etc. I'm just going to pick each one randomly and then sample from that. So this is kind of an average case distribution over circuits. And what Boyce et al. Did is they conjectured that this is hard to simulate classically. Okay, and but now when they made this proposal, there was something that was a bit dissatisfying about it from a complexity theoretic perspective. Namely, the thing that was dissatisfying about it is that they were missing some of the evidence for hardness that we had for boson sampling. So namely, if you were to look kind of in this picture here, the situation for random circuit sampling was as follows. So you can show using standard techniques that this problem is sharp P hard. Computing the output probabilities is hard in the worst case, both exact and approximate. But there was no known proof of average case hardness for this proposal at all. And this left things very unsatisfying because in some sense, the whole reason that boson sampling was kind of convincing, that the reason this conjecture looked reasonable is because we knew there was average case hardness in the exact case. So we knew that this distribution was hard in some way. We just didn't know how to prove that this hardness was kind of robust to approximation. So yeah.
Bouland has a polynomial time randomized approximation scheme. So why do we still use that?
Okay, so the question is, the permanent has a polynomial time randomized approximation scheme. So does this invalidate this conjecture? So critically, that only works for permanents with non-negative entries. The key here is, like in almost everything we've been talking about, the permanents we're talking about here have positive and negative entries. So the Jerram-Sinclair-Vigoda FP task for it fails. Yeah, so this is, and in fact, this is why, in fact, that algorithm kind of lives here. In fact, it's even a worst case thing for non-negative matrices. So again, the reason this conjecture is reasonable is that we're really talking about computing things that have lots of cancellations. It's the same as the first lesson. Good question, though. Yeah.
Last step, you sample an output of the circuit.
Yes, that's right. In the last step, you sample an output. So the question is, so this is the task. And in order to justify the hardness of sampling from this output distribution to total variation distance error, by copying the proof from last time, it would suffice to conjecture it's hard to compute the output probabilities of random circuits, approximately and on average. Yeah.
Task is given a circuit with a sample like that. So the task is only the third.
Yeah. So the task is the task is given a random circuit C drawn from this distribution. It's some kind of Haar measure on your kind of gate pattern. Sample from its output distribution. To small, to epsilon total variation distance error. That's the formal computational task. Okay. So that was the status of the Boykshaw et al. Paper. And that was the status of the Boykshaw et al. Paper in 2016. So this proposal was out there, but it was kind of missing some of the key justification for its complexity theoretic hardness. So, so now the kind of next thing that happened, the evolution of this, was a paper that I wrote with Bill Pfefferman, Chinmay Nurki, and Umesh Vazirani. What we did is we showed that there is a form of exact average case hardness for quantum random circuits. Namely, what we showed is that it is sharp P hard to compute the output probabilities, or sorry, yeah, to compute to exactly the output probabilities of circuit C drawn from this exact measure. So it's you know, kind of the Haar measure on your on any fixed pattern of gates. So in other words, what our contribution was to fill in this thing that was known for boson sampling in this kind of natively quantum case in the case of random quantum circuits. So this effectively took the Google proposal and kind of brought it up to the same level of complexity theoretic evidence that we had for believing boson sampling is hard. So we now knew that there is some form of average case hardness in this distribution. And in fact, our initial proof showed that it's hard to compute something very close to the output probabilities of these circuits, kind of good enough for these supremacy results to hold. But there was subsequent work of Movasag also contributed to this line and kind of removed some of the kind of minor technical caveats of our initial construction. Yes? Sure.
So does that also apply that it's hard to sample? I mean, calculating the probabilities is slightly different than actually sampling.
Oh, yeah. So the question is, does this imply it's hard to sample? So no, it doesn't. So this conjecture is what implies it's hard to sample, assuming pH doesn't collapse. Okay, but nobody knows how to prove this conjecture for any of the supremacy proposals. But the kind of best that complexity theorists have been able to do is prove average case exact hardness and worst case approximate hardness. But no one knows how to combine these in a single proof. Yeah, if you did, then this would actually show that approximate sampling from quantum circuits is hard, assuming pH doesn't collapse, which would be kind of like the holy grail of complexity to base, you know, quantum advantage on non-collapse of pH. Yeah, sure. Yeah. Oh, so the question was, do we have worst case approximate hardness? Actually, we do have worst case approximate hardness for random circuit sampling, as long as your pattern of gates is chosen in some way that it allows for some form of universal quantum computing in some way. So that's actually doesn't turn out to be a major barrier.
But also it should be mentioned that even if this conjecture holds, then that would show that it's hard to sample with total variation distance, which is small.
Yes,
but this
that's
is
correct.
also a highly non-realistic
Yes.
thing to expect if we
that's
have
correct.
noise.
Yeah. I'm going to discuss that when I get to describing what Google did shortly. But yeah. Oh yeah. So the question is, do I need to care about whether this is gap P hard or sharp P hard? Yeah, you could put gap P hard in any of these quadrants. But actually, we only need sharp P hardness for the proof. But yeah, it's in this case, it doesn't matter. Remember, gap P and sharp P are basically the same when you're talking about them as a normal complexity class. They're only different under approximation. So yeah. So you can say gap P functions are still sharp P hard to approximate in the worst case. Like that's also true as well as them being gap P hard. Yeah.
I would like to ask whether what is the notion of approximation? So it's clear that you aim for total variation distance error approximation.
Yes.
Previously you talked about multiplicative approximation.
Yes.
So
Yeah. Okay. Yeah. So that's a great question. So what type of error do you need for the conjecture? The conjecture, the native form of the conjecture is if you're talking about total variation distance epsilon, the native form of the conjecture is that it's hard to compute them to additive error something like 1 over 2 to the n, kind of like epsilon over 2 to the n times, it's basically something like this. You would need it to be hard to compute them to this amount of additive error. So most of these probabilities are order 1 over 2 to the n. Okay, so the kind of point is that if you have anti-concentration, there's this property called anti-concentration, which is something like most probabilities if you pick a random circuit and look at a random output, most of those will end up being more than some constant over 2 to the n. Then that means that this error is, that means that you can turn this conjecture, which is kind of natively an additive conjecture, to a multiplicative conjecture. The multiplicative conjecture would be the same thing, that it's hard to compute them, to multiplicative error, 1 plus or minus 1 over Pauli. So what anti-concentration is doing here is it's kind of playing a supporting role. It's saying, if you have kind of some form of average case hardness, then you can convert the average case hardness that's natively additive from your experiment and turn it into a multiplicative form of hardness. Okay? And one of the advantages of random circuit sampling is that for RCS, it's known that anti-concentration has been proven. So this is a result, it goes back to Brandau, Harrow, and Horodecki. There was also a recent paper of Harrow and Mehraban that showed that for this kind of very specific form of circuits for Google's experiment. But on the other hand, for boson sampling, actually anti-concentration is open to prove. Actually, Aronson and Arkhipov did some numerical experiments, and they showed that numerically it looks like it anti-concentrates, but there's not a proven kind of asymptotic statement of that result. So so in short, if you were to try to kind of plot what these, if you wanted me to make a comparison between the different proposals, kind of what's happening is, let's say we want to compare these. They say which of these have average case exact hardness, which ones have, all of them actually have the worst case approximate sharp P hardness, so that's not, all right, so but I'll put that in there. Worst case approximate. Which ones have average case approximate, and which ones have anti-concentration. The status of affairs was that boson sampling, it had this average case exact hardness and worst case approximate, but anti-concentration and this were open. So when random circuit sampling was proposed, we knew anti-concentration, but we didn't know exact average case hardness. So now this is what we filled in our work with, in my work with Bill Pfefferman, Chinmay, and Umesh. And then there are other proposals such as IQP, and these proposals had looked the way that RCS did when it was proposed as well, which is to say they didn't know any average case exact hardness, but they only knew worst case hardness and they knew anti-concentration. So this was like the Bremner, Montanaro, Shepard paper from 2016 about average case IQP was exactly in this framework. So this is kind of the landscape of them. So when we kind of showed this result, this meant that random circuit sampling was the first result that had kind of every box except the one no one can fill in, right? So that's kind of the status. So in some sense, it raised it up to the kind of the best we can do so far. Now, actually, you can using our techniques we developed, you can actually show a form of average case exact hardness for some variants of IQP. Slightly different than the ones they originally proposed. So I'll say that actually our techniques were very general, so that they did carry through. But this is kind of the status of what's known. So you can now see that really the main open column is this average case approximate hardness. We just don't know this for any model. Okay. Yeah, exactly. We don't know this. We don't know strong enough average case approximate hardness to tell us anything about hardness of sampling the total variation distance. Yeah. And as Dorit mentioned earlier, the experimental results are even far from this as well. So I'll explain this shortly. Okay. And the proof of this statement that's worse about average case hardness for random circuits, unfortunately, I don't have time to go into it because I want to talk a bit more about Google's experiment. But the proof of it is, you can think of it as it's a form of Liptons Theorem for groups instead of linear subspaces. So what do I mean by this? Well, what were we using in the permanent proof? We're using the fact that we could take our worst case matrix and we could add in a random matrix that was like a one-time pad, right? So that was kind of using the fact that matrices form a linear subspace. So you can actually add in something. But if you have quantum gates, there's no such thing as saying that your quantum gate is going to be your old gate plus t times some random gate. Like that's because you can't add gates. Adding unitary matrices does not yield unitary matrices. So what we kind of need to do is we need to say, okay, like what's kind of the right analog of this transformation for the quantum case? And the key ended up being something like the following. So what our transformation was instead is we said, here's how you're going to scramble a circuit. Given some gate G, pick a Haar random gate H, and let G of theta be equal to your old gate G times H times e to the minus log of H times theta. So what's going on here? Well, the point of doing this is that if you pick it like this, then G of 0 is your original circuit, but G of 1 is H. G of 1, G of 0 is H. Sorry, I flipped this. And G of 1 is your circuit. So kind of what we've done is you take your original gate, you scramble it entirely, and then you like dial it back a little bit. You dial it back by some angle theta in the direction of your original gate. That's what's happening here.
Is that right?
Sure.
Yeah, G of 0, can you say GH? It's GH, no?
Oh, G of 0 is GH. Yes.
It's also right.
G of 0 is GH, which is also random. Yes, that's right. And G of 1 is equal to G. Yes, thank you. So the point is that G of 0 has this marginal property. G of 0 is randomly distributed by the left invariance of the Haar measure. And what we also showed is that G of theta is close in total variation distance to the Haar measure as well. It's something like order theta close to total variation distance to the Haar measure. So this is kind of our analogy of the marginal property. Then the other thing that we do is we show that the output probability of the circuit is some low degree polynomial in the gate entries. So this gives us this low degree polynomial structure. And then our proof works very similarly to the Lipton case, because what we do is we pick a whole bunch of small thetas. We compute, the circuits that correspond to those small values of theta look really close to random. So our algorithm can solve them by this Lipton argument. But then because there's this low degree polynomial structure, we can interpolate back to G of 0. Now there are a lot more technical details to be worked out in this proof. It's much messier than the other case, so I'll point you to the paper for those details, but this is kind of the very high level idea of what's going on. Okay, great. So I now have maybe half an hour or so left. So I'm now going to move on to describe the next challenge in the the next challenge in quantum supremacy, which is to verify what happened with your experiment. And by defining the way they're verifying it, I think it will make it a bit more clear kind of what those graphs Gail showed in the last talk are really corresponding to with their experiment. Okay, so that's kind of the state of knowledge of what we know about hardness of these experiments. What about verifying them? So if I'm sampling from a probability distribution on 2 to the n strings, how many samples does it take for you to know that I'm sampling from the exact distribution I claimed? Well, if you were to try to naively verify it, if you were to actually try to characterize the distribution of your experimental device completely, then this would require something like exponentially many samples, and then also exponential amount of computation time as well, right? So why is this? This is just because if you have a black box distribution, and you want to test if it's close in total variation distance to some other distribution, in general, this takes exponentially many samples to verify that. I mean, just because, just estimating, making an empirical estimate of your output distribution that's of high enough quality to tell if you're this close in total variation distance is a very difficult task. And it should be kind of clear that this type of naive verification is not going to be feasible on near-term devices, because 2 to the 53, if you have a 53 qubit device, 2 to the 53 is a lot of samples. It's like 10 to the 15th samples. It would take you like decades to fully characterize the output distribution of something like Google's quantum computing device. So what was actually proposed for verification is actually kind of what I call like a bit of a compromise form of verification. They're considering a form of verification where they only take polynomially many samples from the device, but they still spend an exponential amount of classical computing time to check them. So here they're using the fact that they're in some particular kind of Goldilocks regime where these computers are big enough, that this classical computing time is challenging to achieve, but not so big that it's entirely impossible, right? And okay, so now what can you do with poly-event samples and a lot of computing time? Well, what they actually propose to do is to take some kind of coarse statistical store of the output distribution. The particular statistical score that they considered is something that they called the cross entropy. So I'll define what the cross entropy means. So the cross entropy between two distributions, namely the experimental distribution of your device and the ideal distribution of your device, it's a formula that looks like the entropy. So that's you sum over all output strings of the experimental device's output probability and log of the ideal device's output probability. So this is, it's something that looks like an entropy, but it's kind of like, you can think of this as kind of like it's an inner product between your experimental distribution's output and the log of the ideal distribution's output. So you can write this. You can just also write this as an expectation over y drawn from the experimental distribution of the log of the ideal distribution's output. So the way that you can compute this is very simple. So because it's an expectation value over your experimental distribution samples, the way that you compute it is you just sample many y from the device, okay, and compute the average of the logs of the ideal output distributions. So you can see why this takes exponential computing time. So you just take some few numbers of samples for a device, but then you have to use a supercomputer to check, what should the ideal probability of the string should have been. And I think the right way to intuitively think about this score is it's really saying something like this. It's saying, I'm trying to check that most of the time I sample things that are heavy in the output distribution of my circuit. That's really what the score is kind of trying to say. And furthermore, this score obeys some sort of concentration of measure, it turns out, because of some special properties of the ideal output distribution. It turns out that we can actually, that two things happen. First is that it actually takes very few samples to estimate this probability, this cross-entropy score. And second, we know what the ideal cross-entropy score was. So this is, I'll just say this is special facts about the ideal distribution. Tells us that we actually know the value of the cross-entropy. Oh yeah, that's right. The entropy is just the entropy. Cross-entropy of a distribution with itself is just the entropy. Exactly. So the basic idea is okay. You can also, it turns out, you can also compute the cross-entropy of the uniform distribution and the ideal. And this is actually equal to the ideal score minus 1. So what they propose as their score, and the things that you're seeing on some of their plots, or some minor variant of it, is they said, let's just consider the cross-entropy difference. Consider this quantity, which is cross-entropy difference, which is just equal to the cross-entropy of the same things minus the cross-entropy of the uniform to dn. So this is a score which is equal to 1 if your sorry, I switched the order. This is a score which is 1 if your experimental distribution is spot on. The score which is 0 if your experimental distribution is the uniform distribution. And what Google's claim is that if we make an experiment that scores well on the cross-entropy difference, then they claim that this implies quantum supremacy. Okay, so this was the situation in 2016. And if you look at this, it looks a bit weird. So there seems to be a bit of a disconnect. So what's somewhat unsettling about this proposal when you first look at it is that there appears to be a disconnect between this verification that they're talking about and this hardness of sampling that we talked about earlier. So before we were talking about hardness of sampling the exact right distribution in terms of total variation distance, whereas this is saying, well, we're actually not going to check that. We're just going to kind of compute some very coarse statistical score of our distribution. And what does this score have to do at all with kind of the original supremacy argument? So when they proposed this, there was some sort of gap, between the hardness arguments and verification. Now, why did they think that these things connected? Well, the reason they thought they connected is that Google had this conjecture. They basically conjectured that the output distribution of their circuits was a convex combination of the ideal state and the maximally mixed state. The maximally mixed state is just uniform noise. So why did they conjecture this? Well, they conjectured this because they said something like this. Well, let's assume we had an IID error model, like IID depolarizing noise, IID amplitude damping. There are many forms of noise models, but let's assume we have a very simple one. Then the intuition was that if there was an error in this random circuit, then it should completely decorrelate the circuit's kind of output probability distribution with the ideal one. And therefore, it should look like random noise for the purposes of the score. Right? And if you take this kind of very strong assumption, then you can very quickly check that a state of this form would achieve cross-entropy difference alpha. Right? The reason is just by linearity. Right? This score is something that's linear in the device's output distribution. Right? This is the device's, the experimental output distribution. So if you fill in here, alpha times d-id plus 1 minus alpha times uniform, 1 over 2 to the n, you'll get exactly alpha out of this formula. So the way that they were thinking about is they were thinking that cross-entropy difference alpha basically corresponds to fidelity alpha. So therefore, if alpha were big, then it would be close in total variation distance. Right, so I'll write this down. So therefore, if alpha were 1 minus epsilon, you would be order epsilon close in total variation distance. Okay, but if you look at this, if you look at this, there's something a little unsatisfying about this. So this does connect you to total variation distance, but it only does so under this very strong assumption. And this assumption is almost the same as assuming the device worked, right? Because we're assuming that we had the ideal thing in our grasp, and it's just when there is an error, it slipped away, right? So, and they're also assuming when there is an error, it gave you no score on this metric at all, right? So that was the situation in 2016. Now, it turns out that you can also show that it's maybe not quite that bad. You can also show that this score connects to total variation distance if you make a slightly milder assumption about the noise. Okay? So in particular, what we showed is that if the noise in the system is such that the entropy of the experimental distribution is more than the entropy of the ideal distribution. And this would occur, say, if this would be true if you assume, say, IID depolarizing noise. Then that implies that a cross-entropy difference score of 1 minus epsilon actually implies your total variation distance will be less or equal to order square root epsilon from the ideal. Okay, so in other words, this is saying that if you're willing to make a different noise assumption, that is, that my noise in my system increases the entropy of my samples, then I can actually prove to you that the total variation distance is close. So if you got a really good cross-entropy difference score, then you would actually get a total variation distance bound and therefore connect to the supremacy arguments. And the proof of this is really simple. The proof of this is actually, it's quite elementary. It's Pinsker's inequality, which says that the total variation distance between two distributions is less or equal to 1/2 the square root of the KL divergence between the experimental and the ideal. And the KL divergence can be written as the cross entropy minus the entropy. And what this means is if you assume that the output of your experiment has bigger entropy than d-id, you can replace this in this equation. You can replace this last term with the entropy of the experiment. in this inequality. And you can show, just by a straightforward calculation with these things, that this thing would then be equal to epsilon, because this thing is equal to the cross-entropy difference score. Actually, it's 1 minus the cross-entropy difference score, which is then epsilon. Also, I might have messed up. I don't remember. I always say it's the 1/2 in Pinsker's inside or outside. But OK, anyways. But that's essentially the proof. Actually, Brandau noted this independently of us as well. But what this is kind of showing is that if you are willing to make some noise assumptions, then this cross-entropy score actually does certify supremacy if you also believe the average case approximate conjecture. But actually, if you had other forms of noise that did not increase the entropy of your samples, then this argument would be invalid, right? So in short, it seems like the validity of their kind of supremacy tests will end up hinging on what kind of characterizing the noise that's present in their device. OK, so I have just maybe 15 minutes left, so I'm going to go on to tell you what Google actually did. OK, and then you can then, I'll talk about what Google actually did, and then I'll talk about another way of justifying supremacy of the Google experiment in a kind of independent line of work of Aronson and Chen and Aronson and Gunn. OK, so great. So all these arguments said something like this. If you assume that you can show average case approximate hardness, and you assume that you have something like a kind of nice noise model, then then you get that if you have cross entropy difference more than 1 minus 1 over Pauli, then you've demonstrated supremacy, right? So now, what happened in the Google experiment? In the Google experiment, what they actually did is they performed this experiment on a superconducting qubit device of 53 qubits. They picked random circuits and sampled from them. They computed the cross-entropy difference score. They also computed a slightly different variant of the score that I'll describe later, but they computed the cross-entropy difference score as well. And what they did is they ended up showing, they found a cross-entropy difference of their experiment is around 0.002. In particular, they showed it's greater than 0.001 with 5 sigma confidence. OK, so now, as is oftentimes the case, there is a gap between the theory and the experiment. So the gap here is that the theorist asked for fidelity 1 minus 1 over Pauli. So we asked for 99% cross-entropy difference score. Well, I mean, we asked for that, but if you want to use the arguments in our paper directly to argue for quantum supremacy, they're
You need to argue for quantum hardness?
to argue for quantum hardness using the sharp P average case hardness route. Okay, so if you're going to flow your argument through our paper and through the Aronson-Arkhipov style arguments, then you have to be scoring very high in cross-entropy difference, right? But what they actually were able to do is achieve a very small cross-entropy difference. Okay, so great. So this kind of there's a gap here. Okay, so how can we? How can one theoretically justify that this is actually achieves quantum supremacy through some of these arguments? Okay, so how do you plug the gap? There are basically 2 ways to plug the gap. The first way is to make a stronger noise assumption than we would want. So if you assume their original noise model if you actually assume this noise model, and let's say that alpha is 0.002 in this noise model because it's just directly your cross-entropy score, then what that means is that actually you can actually argue for supremacy you can argue for supremacy by the average case arguments. By these average case sharp P arguments. And the proof is really simple. You just need to rescale the output. You just need to rescale the output probabilities of your experiment, right? Because remember how our argument worked? It said, okay, if we had the classical simulator for this device, then we could compute the output probabilities, and that looks like it's sharp P hard. And here, what you'd be doing is you'd be computing, what that argument would then say is your BPP to the NP algorithm would then instead compute alpha times your ideal output probability plus 1 minus alpha times 1 over 2 to the n. And if you compute this quantity, you can easily infer P-id if you know the value of alpha, right? You're just enacting some linear transformation on your output probabilities. And this is the way that this is actually written up in the supplemental material of the experiment. But now there's actually an entirely different way of trying to justify the supremacy of this experiment. And the second way that you can do it is by making a stronger complexity assumption. So the second way that you can plug the gap is with stronger complexity assumptions. And this is actually 2 works of Aronson and Chen, and also work of Aronson and Gunn. Actually, this one is concurrent with Boyk-Chodal, and this one is just this year. So in particular, what they did is they, the insight of this complexity assumption, the question that they asked here is, can we directly justify the hardness of achieving these scores? Like, is there a way, this way of justifying the hardness seems a bit indirect. It's like, okay, we make this noise assumption. We then compute the probability by the Stockmeyer reduction. We then we make an average case approximate hardness conjecture. We then use Stockmeyer counting to collapse the pH, right? So it's kind of, you're snaking your way through a lot of things. Is there a way to just say directly why you think the score is hard? All right. And the answer is basically yes, if you make stronger assumptions. And the assumptions all have the following form. So I'm going to describe the assumption that they made for their original paper of Aronson and Chen. And there's an analogous version by Aronson and Gunn for Google's, that more precisely matches the Google experiment, but it's very similar flavor. So I think that the older one actually illustrates it more clearly. So what they did is they said they defined a task that they called heavy output generation. In retrospect, I'm going to call it heavy output generation, or HOG. I'll give it a parameter b, and b is a parameter between 0 and 0.5. This will end up being some bias in the experiment. And the basic idea of heavy output generation is it's considering the following task. So it's saying, so instead of considering the cross entropy difference, let's consider taking the expectation value of a different function. So let's draw a sample from the experiment and compute whether or not the ideal output probability of that sample is more than the median of the ideal distribution. All right, so what's the score if the experimental distribution were uniform? What would the score be? So let's call this the HOG score of the experimental distribution is defined to be this. So if you took the uniform distribution, what would its HOG score be? What fraction of the elements that you sampled would be above median weight in the output distribution? Okay, I had a guess of 0. Any other guesses? Okay, well, I'm going to claim that it's a half, right? Because exactly here, delta, I mean it's 1 if it's more or 0 if it's less. Okay, if you put in plus minus, it would be 0. But why is that? Well, it's because basically half of the elements are heavy in the output distribution, half of them are light.
Aren't they all the same probability?
No. The point is that, no, they're not the same. This is the probability in the ideal output distribution. So I give you a random circuit.
So the
Yes.
experiment was uniform and the ideal was...
And the ideal was the ideal from the circuit.
Okay.
Yes, exactly. All right. So, and it turns out that you can compute that if you had the perfect experiment, this would actually get a large and positive score. There's some closed form solution. It's maybe, I forget, it's 1 minus 1 over E, or anyways, it's some constant that's more than 2/3. So what Aronson and Chen suggested is they said something like this. They said, okay, so what we're going to do is we're just going to conjecture that it's hard to get to score well on this measure. So they define the heavy output generation task would be to, the task is to achieve that the expected value over a random circuit drawn from this distribution of the Hogg score between your device and the ideal, the ideal is a function of the ideal circuit. The challenge is to sample samples such that your Hogg score is more than a half plus some bias B. They initially said that this quantity was 2/3, but you can frame it in terms of any amount of bias that you want. Okay, and then they conjectured that this is hard. This is hard for BPP machines. And the other thing that they did is they showed, well, actually, if you made a very strong complexity assumption, then you would be able to justify that this is hard for classical computers. So in particular, they made the following assumption, which they called the quantum threshold assumption, or QOTH. And what it says is the following. It says that suppose that no BPP algorithm can achieve an expected Hogg score of better than a half plus omega of B over 2 to the n. Then they showed that if you believe QOTH, then this implies that Hogg is hard for classical machines. The proof of this is a very straightforward reduction. It's just, okay.
Sorry, Adam.
Yeah.
I don't understand what the statement is.
Sure.
What is the assumption?
All right. The assumption is there is no classical polynomial time algorithm that, given a random circuit C, if you were to compute its Hogg score, this is an average case Hogg score with a choice of C, it could not achieve a bias over random guessing that's better than B over 2 to the n, where B will end up be related to whatever bias you end up actually getting in the score from the experiment.
What's the difference?
So what's different? Yeah,
That's
exactly.
Assuming that Hogg is hard?
Yeah. What's
This assumption is, well, this is basically assuming Hogg is hard.
But
Yeah.
why do you lose a 2 to the n? Why?
The reason you lose a 2 to the n is that you say, okay, so how do you prove it? You basically say something like that.
I think the question is, what is the difference between the two statements, between the assumption and the conclusion?
So,
They both seem to have the same sort of equation, except one of them has the 2 to the n.
yeah, so, sorry. Oh, wait, okay. Actually, I messed it up. So thanks for pointing this out. So this algorithm is a slightly different form. What this algorithm does is no BPP algorithm can, given a random C, determine if 0 to the n is above or below median in C's output distribution, and be correct with probability more than this. Okay, sorry. So I completely misstated it before, so thanks for catching this. So the difference between this is that this hog task is naturally talking about sampling. This hard task is saying it's hard for a classical computer to sample something that gives you a hog score. And this quantum threshold of something is about a different task. It's about a task of something that looks like computing the output probabilities, or rather deciding if the output probabilities are heavy or light. So this is really saying that, what this is saying is that if you believe it's really hard for a classical algorithm to guess if an output was heavy or light, like really hard, like with a tiny amount of bias, then it would also be hard to sample. All right? And now, yeah. This is an average case assumption over C. So given a random C, determine if this is true and be correct with probability this on average over C. Yeah, average over C, and if it could be a randomized algorithm, sure, yeah.
So Adam, you need to decide what you want to spend your last minute on.
Sure. Yeah, so great. So I'll just kind of close with kind of the following statement. So when Google actually ran this experiment, they computed a slightly different metric that they called the linear cross entropy, which is basically the expectation over y from the experiment of the, instead of the log of the ideal output probability, just the ideal output probability. They called this the linear cross entropy. Now, that term is maybe a little silly because something's not an entropy without a log. This is really an inner product between the distributions. And for linear cross entropy, you can make a very similar assumption that, you know, if you think it's really, really, really hard to estimate output probabilities of random circuits, then you can believe that achieving this score is hard. And let me just say that the reason this quantum threshold assumption is not entirely unreasonable is that the best classical algorithms, they achieve, they can guess if a string is heavy or light. With probability at least a half plus something which is order 1 over 2 to the m, where m is the number of gates of the circuit. So this comes from some kind of Feynman path integral things, like the way you prove BQPs in p-space. So what you should really view this Quoth assumption is it's kind of a fine-grained hardness conjecture. It's saying we have algorithms that can compute it with bias 1 over 2 to the number of gates. And we're now conjecturing that that algorithm is kind of tight. That because in our circuits we can have more gates than number of qubits, we can if you conjecture this is really kind of the best algorithm, then you already believe the hardness of achieving kind of small constant biases on the experiment. So this is kind of where I think the kind of objective reality of the justifications for the Google experiment stands. Like one either has to make a stronger noise assumption, like this noise assumption, and then you connect to average case hardness arguments. Or one can make a kind of more fine-grained assumption about computing output probabilities of these random circuits. But those are, to my knowledge, the existing justifications for hardness of Google experiment.
All right. Thanks, Adam.
Right. Thanks.
Any final questions before we send Adam to regain his strength for the one question? Sure.
Yeah.
What is the weakest point in the argument?
What is the weakest point in the argument? You either, here you're making this assumption, which is I think it's a very fine-grained assumption. I'm really not sure if this is true. This assumption has only been made for a few years, and people haven't looked at this very carefully, because this is an average case assumption. These algorithms work in the worst case. You might worry that there's a better average case algorithm. In fact, some variants of this Swath assumption are false in boson sampling for some kind of non-trivial reasons I'm happy to discuss over the break. So there's just kind of some care has to be taken in this area, though to my knowledge, nobody knows how to break these. And then here the assumption is you have to make this very strong noise assumption plus average case approximate conjectures. This noise assumption is certainly false as exactly written, but it seems reasonable that it's approximately true, and determining to what degree this would be approximately true in an IID error model or something like this, I think is a nice open question as well. So I mean, yeah, there are assumptions that are made in all of the arguments, and yeah, you can take your pick as to which ones you're more or less comfortable with.
All right, so as I said, this was the last technical talk. So we're going to thank Adam again, but we're also going to thank all the other great lectures and great courses that we had. Thomas, Dorit, Sandy, Boaz, and our TAs, of course, Andres and Chinmay. Who am I forgetting? I said Dorit. Let's thank Dorit again also.